So, welcome again to the new lecture on solar photovoltaics principles, technologies and materials. So, we will just do a brief recap of the last lecture. So, in the last lecture we looked at things like, so we wanted to establish a mathematical framework. So, we first looked at assumptions for p-n junction analysis. So, we assume that there is no generation of carriers in the semiconductor, there is a depletion region, there is no generation recombination within the depletion region, the conditions are low level injections, and within the bulk of the semiconductor the field is flat, the bands are flat, as a result electric field is equal to 0, and within the bulk of the semiconductor the change in the majority carrier concentration with respect to distance is equal to 0, and then we made the depletion approximation appropriately, and for then we wrote from the continuity equation the minority carrier equations, and these equations were for the holes it would be dp del 2 delta pn by del x2 minus delta pn divided by tau p, and for electrons it would be dn del 2 delta np by del x2 minus delta np divided by tau n. These were the equations that we looked at in terms of, so basically what you have here is, because you are only considering the diffusion of carriers and recombination, and we also said that the total current within the semiconductor J total was equal to Jn plus Jp at any given x, okay. And what basically it meant was, this is identical to saying that the current you have at minus Wp plus Jp at Wn also makes up this relation, because as we saw that if you have the total current, so if you have this as a depletion region, the total current goes like this, sorry, it goes like this, and similarly on this side the total current goes like this, and then it goes like this. So, basically we are saying that, so this is for if this is p side, this is n side, this would be whole current Jp, and this would be the electron current Jn. So, basically that if the total current is equal to Jn plus Jp at any given position, it also means that this is equal to Jn and Jp at this point and Jn and Jp at this point, or you can say it is equal to Jn at minus Wp and Jp at plus Wn, because of depletion approximation, that nothing goes in, whatever goes in depletion region goes out, okay. There is no generation recombination within the depletion region. So, basically what we have to do is that we have to solve equation for delta Pnx and delta Npx in order to calculate the currents, and that is what we were doing. Finally, what we did was we calculated the junction potential. The junction potential Vj was equal to Kt by Q, which is equal to Vbi. So, in equilibrium it will be equal to Vbi, in non-equilibrium condition it will be equal to Vbi minus Va, and this is equal to Kt of Ln Nn at Wn, which is the majority carrier concentration, divided by Np at minus Wp. Similarly, you can write the expression in terms of holes, which will be equal to Kt divided by Q Ln Np Pp at minus Wp divided by Pn at plus Wn, right, from the same, because if you recall in the previous, we took the electron term, we could have taken the whole term also. If you take the whole term, then you can do the similar calculation for electric field using the Einstein relation from the whole equation. We use the electron equation, that is why we have everything in electron thing. So, now let us go forward on this. So, in the minority, so if you want to talk about the minority carrier concentration, assuming that we have low level injection conditions, if you have low level injection condition, we are saying that delta Nn is equal to delta Pn, and this delta Pn is much smaller than Nn naught, okay. So, so the perturbation in both is similar, but this perturbation in majority carrier concentration is very small, whereas in case of minority carrier concentration, so this delta Nn is very small as compared to Nn naught. So which means Nn naught is virtually constant, right. However, this delta Pn is nearly comparable to Pn. As a result, minority carrier concentration changes. Okay. So since delta Pn is large enough as compared to Pn, but it does not affect the majority carrier concentration, these conditions are called as low level injection, because you are not injecting too many majority carriers, you are injecting mostly minority carriers. So if that is true, then from the previous expression where we wrote that Vj is equal to Kt divided by Q ln of Nn Wn at Wn divided by Np at minus Wp, I can now flip this equation, change this equation. So if I write in terms of electron concentration, it becomes Nn at Wn divided by Np at minus Wp is equal to exponential of Q into Vbi minus Va divided by Kt, where Vj is equal to Vbi minus Va. So now using this equation, if I flip it over, I can get Np at minus Wp is equal to Nn Wn multiplied by exponential of minus Qv by Vbi divided by Kt into exponential of Qva divided by Kt. What is Nn Wn? Nothing but Nn naught, right? It is nothing but Nn naught. Similarly, you can write an expression for hole concentration also. So now if I move forward, at thermal equilibrium, if I say Vbi is equal to, this we derived earlier, that Vbi was equal to Kt divided by Q into ln of Na into Nd divided by Ni square, and Na is equal to Pp naught and Nd is equal to Nn naught. So this was basically, if you remember, Na into Nd divided by Ni square. Na is equal to Pp naught, Nd is equal to Nn naught. So I can calculate a relation for Vbi. Now if you substitute this, what you get is a relation. So you just need to now substitute. If you do that, you get a relation for Np at minus Wp. Np at minus Wp turns out to be Ni square divided by Pp naught. So this is hole concentration on the, this is electron concentration on the p side at the edge of depletion region. So it becomes a minority carrier, right. So minority carrier concentration on the p side is equal to Ni square divided by Pp naught exponential of Qva divided by Kt. Suppose Va was equal to 0, then this will be equal to 1, then this will be nothing but, if Va was equal to 0, then what you get is Np is equal to Ni square divided by Pp naught, which is the minority carrier concentration in a normal N or P type semiconductor. Similarly, if you do it for holes, you will get the same answer. Okay. So basically, I have got the concentration of minority carriers in terms of bias that is applied. So Np at minus Wp is equal to Ni square divided by Pp naught into exponential of Qva by Kt, and I can see that if I increase the applied bias, then my minority carrier concentration also increases exponentially, which means my current should also increase exponentially. I am seeing a trend here. Similarly, you can write for, so now we have gotten so we know that since Ni square divided by Pp naught is equal to Np naught, okay, Ni square divided by Pp naught is equal to Np naught at 0 bias, right. This is the equilibrium carrier concentration. So I can replace this here. So Np at minus Wp is equal to Np naught into exponential Qva by Kt. So if Va is 0, then Np at minus Wp is equal to Np naught. Now I can write what is delta Np, the change in carrier concentration. So delta Np at minus Wp is equal to, delta Np at minus Wp is equal to Np at minus Wp minus Np naught with respect to the original one. So this is the So essentially basically it is NP minus NP naught. This is at t is equal to 0. This is at some t after the perturbation has been made. Okay. So this is straightforward. Similarly, if you do the same analysis for holes, you will get delta Pn at plus Wn is equal to Pn naught into exponential QVA by kT minus 1 using the similar analysis. Now moving forward, so you now need to solve these equations to get the currents. Okay. So for that, first we make what we call as long base assumption condition. Long base diode assumption basically means that we need to get the final boundary conditions to solve. Final boundary conditions on the excess carrier concentration in the, because remember we have got the expression for delta P, but we also have the recombination term in the minority carrier that we wrote earlier, the continuity equations. So we actually need to solve those equations, alright. So for that we first need to assume that bulk regions are very long, okay, bulk regions are very long in comparison to the depletion region. Secondly, since tau n and tau p are finite numbers, there is a finite lifetime of carriers. The carriers do recombine eventually, okay, at some point they do recombine. So we can say that delta Pn at plus infinity is equal to 0 and delta Np at minus infinity is equal to 0, which means whatever carrier concentration, minority carrier concentration you had at the boundary of depletion region with respect to bulk region, it goes down to equilibrium concentration eventually, alright, because the perturbation becomes equal to 0. So if that is the case, we now do, so basically what we are saying is if you plot the minority carrier concentration in the bulk, it goes like this. So this is N or P. So if this is the edge of one depletion region, that is Wn, another edge of depletion region, this is minus Wp. So I can say that so if you have bias that is equal to 0, if your bias is equal to 0, then this is Np naught if this is P side, okay. If this is N side, then my Pn naught is somewhere here, they won't be equal, so this would be Pn naught. So when bias is equal to 0, right. So this blue color means Va is equal to 0, bias is positive. When bias is positive, then they have exponential dependence. So this varies like this, and similarly it varies like this, right. Exponential behavior is there, you can see from the equations. So this is for case which is Np for Va greater than 0, and this is for Pn for Va greater than 0, right, and this value would be given by the expression that we wrote earlier. So this would be equal to Pn naught exponential of Q Va by Kt, and this value will be given by similarly Np naught into exponential of Q Va by Kt, alright. This is simple straightforward mathematics, there is nothing too clumsy about it. And if you now want to plot the, sorry, if I use a different color now here, if I use a purple color for the negative bias, this will go as something like that on both sides. This would be the behavior for the negative bias. So this would be for it will eventually go to 0, very close to 0. So this would be for Va that is smaller than 0. This would be for Va smaller than 0. Okay, so you can see that carrier concentration is, there is hardly any carrier concentration in the vicinity of junction in the reverse bias, which means no carriers cross on both sides. So carriers are taken away from the junction, so which means carrier concentration is very small. So no junction current flows when reverse bias is there, and large junction current flows when you have a forward bias. And let us assume for the sake of analysis new positions. This position let us say we define as 0 prime, this position we define as 0 double prime. So on this side we take x double prime, on this side we take x prime, okay. So how do we go about it? Well, so how do we go about it is, first we need to solve minority carrier equation in the bulk regions for delta NPX and for delta PNX, both of these, and then apply boundary conditions, because these are differential equations. So solution requires application of boundary conditions, and then determine Jp at xn and Jn at minus xp, which means at the far ends of the semiconductor device, away from depletion region, from the slope of delta Np at minus xp and delta Pn at xn. Okay, that is what we are going to do, and we know that total current J is equal to Jp at Wn plus Jn at minus Wp. This is, so let us first do the analysis. So now let us look at the minority carrier concentration equation at x is equal to xn, that is at x is equal to, sorry, x not xn, should be Wn. Okay. So x is equal to Wn, that is, so if this is the depletion region, we said that this is x is equal to 0 originally, this is Wn, this is minus Wp. We redefined our coordinates, so this becomes 0 prime double prime, this becomes 0 prime. Okay, so or x prime is equal to 0, this is x double prime is equal to 0. So basically x is equal to Wn means x prime is equal to 0. So when we do that, then we redefine our minority carrier equation, which is dp into del d2 delta Pn x prime dx prime square minus delta Pn at x prime divided by tau p, that is equal to 0. So from this equation is a second order differential equation. The solution of this is delta Pm x prime is equal to a1 exponential of x prime divided by Lp plus a2 into exponential of minus x prime divided by Lp. This is a standard solution for a second order differential equation. Since we know that diffusion length is equal to square root of diffusivity into minority carrier lifetime, we have replaced in this. So you can see that you have a term d, you have a term tau, right. You can take this on this side or you can take this on this side. So essentially if you solve the differential equation, you can take this becomes dp tau p, and dp tau p is nothing but Lp square. Okay. So when you do this, when you do the solution, you get something like that. So basically we need to determine now a1 and a2. How do you determine a1 and a2? By applying boundary conditions. Similarly, you do the same analysis for now boundary. What are the boundary conditions? The boundary conditions are, the first boundary condition is delta Pn at infinity is equal to 0. Second boundary condition is delta Pn at x is equal to Wn, that is at 0 prime is equal to delta Pn naught exponential QVA by kT minus 1. This we have established earlier. Similarly, so from this we can get a1 is equal to 0 and with a2 is equal to minus delta Pn at Wn. Sorry, I just wanted to make here when we are looking at actually Wn. Okay. Wn at minus Wp, similarly here minus Wp and Wn. Okay. So from this we got a1 and a2, and then we can get what is delta Pn at x prime. This is, so it's just substitution now, right, a1 and a2. So if you substitute a1 and a2, you get this. So basically Pn x prime is now equal to Pn naught plus Pn naught into exponential of QVA by kT minus 1 into exponential of minus x prime divided by Lp. Now, So from this we can get what is diffusion current. Diffusion current is nothing but Jp x prime is equal to minus q dp into del of delta Pn x prime divided by dx prime, right. So it is a simple diffusion current which is derivative of delta Pn. Now you need to substitute the value of delta Pn here. If you substitute the value of delta Pn here, you get Jp x prime as some function, alright. It is very simple differential equation, there is nothing complicated about it. If you just keep doing it, what we get is Jp x prime is equal to q dp divided by Lp into Pn naught into exponential of qVa by kt minus 1 into exponential of minus x prime divided by Lp. Substitute x prime by x prime is equal to 0 is equal to x is equal to Wn. So we substitute x prime by x, and what we get is x prime is nothing but x plus Wn, alright. So because x prime is 0 where x is equal to Wn, as a result x prime is x plus Wn. So we have made the substitution, we get the equation for Jp. If you do the similar analysis for electrons, you will get Jn. If you do that, so by doing similar, now at x is equal to Wn or x prime is equal to 0, we know that Jp at the depletion edge is equal to Jp at Wn, that is equal to Jp at W0 prime. So Jp at Wn is equal to q dp by Lp into Pn naught into exponential qVa by kt minus 1. So essentially what we have done is, if you look at the, so basically we have taken this x prime is equal to 0, alright. So when you take x prime is equal to 0, this should be, hang on, there should be one minor mistake here, it should be minus Wn, okay, because you are starting from x. So we are saying that x prime is equal to 0 at x is equal to Wn. So basically x prime will be x minus Wn. So when you take x as Wn, then that exponential factor becomes equal to 0 at the edge of the depletion region. So we get Jp at Wn, that is equal to q dp by Lp into Pn naught into exponential of qVa by kt minus 1. If you do the same analysis, you can get the electron current as well, and so I am not going to go through that, but if you do the same thing, you get an expression for the whole current. So this is what the whole analysis is. You can look at these slides later on because they will be available here, but basically you are doing for the region x prime, x double prime greater than 0 double prime, that is for the region x on that in the bulk region of p side, which means x smaller than or equal to minus Wp. So if you do that, you can calculate using similar logic. Jn at minus Wp is equal to q dn by ln into Np naught into exponential of qVa by kt minus 1. So we got two expressions, one for electron, one for hole. Now you need to just sum them up. So when you sum them up, what you get is this: J total is equal to Jn plus Jp, and J total is equal to q into dn by ln into Np naught plus dp by Lp into Pn naught. So you can see that this is equilibrium concentration, this is dn by ln, the diffusivity divided by diffusion length, this is dp by Lp. So this is for holes, this is for electrons, into a factor exponential of qVa by kt minus 1. This current, you can see that there is no bias dependence here, so you can write this as J total. So I think I have already written it here. So I can write this as, so if you convert the current into current density into current, you can write this as I is equal to I naught exponential of qVa by kt minus 1, and where I naught can be written as q into area, because if you convert J to I, then so because J is equal to I divided by A. So q into A into dn divided by ln Np naught plus dp divided by Lp into Pn naught. This is the reverse saturation current that you get at 0 bias or negative bias, or at negative bias, not 0 bias, at the negative biases. Okay, so it will be minus. So basically when the voltage is very negative, this will be 0. So this will be minus 1. So what you get on the other side is minus I naught. Okay. So this is what basically we get. So we know that what is Np naught and Pn naught, and if we replace them, we get I naught as equal to qa into Ni square dn divided by ln Na plus dp divided by Lp Nd. So it's just so you can further tweak these equations. For example, if Na was a lot larger than Nd, which means P side was more heavily doped than the N side, then this is almost equal to Qa Ni square into dP divided by Lp into Nd. So reverse saturation current is governed by the whole diffusion length, whereas if it was the other way around, so if you had it other way around, Nd much greater than Na, then you can write that I naught will be equal to Qa Ni square into ln dN divided by ln into Na. Okay. So basically this is what the expression for current that you get is. So when you plot it now, so this is the forward current which has a e to power q Va by kT minus 1 dependence, and this is basically the minus I naught you get in the reverse bias. So this is reverse bias, this is forward bias. If this is voltage, this is current. So this is the quick analytical solution of reverse and forward current for a PN junction in forward and reverse bias. Okay. So you can go through these slides again. So basically if I just recap this just for the sake of clarity, what we did was we first worked out the electron concentration in the as a function of applied bias, right, and this is nothing from this is very simple from the junction potential expression. Junction potential can be obtained from the balance between current and diffusion current and drift current, and apply Einstein relation, you get a expression for minority carrier concentration in terms of applied bias, and this you can do for both electrons and holes. So if you do for both electrons and holes, we get Np at minus Wp for electrons, and similarly you can get for holes also, and from Np you can get delta Np. Similarly for Pn you can get delta Pn. These delta Pn and delta Nps are going to be useful to solve the diffusion minority carrier equations. So then we solve the minority carrier equations. So basically that is what we did. We had this minority carrier equation. We just changed the references from x is equal to Wn to x prime. There is no need to do that, but it just makes it a little simpler. So you just solve the differential equation from this, then you apply the boundary conditions for both the regions. From the boundary conditions you can work out the minority carrier concentration at a given position, and then you calculate it at the edge of the depletion region, because there is no point in calculating at any x, because you always know that J total is equal to Jn at minus Wp and Jp at plus Wn. So you just want to simplify that. So you replace x prime as 0. When you replace x prime as 0, this is what you get. So Jpx is equal to Qp dP by Lp into Pn naught exponential QVA by Kt minus 1 into exponential of minus Wn plus x divided by Kt. So at x prime x is equal to Wn, this factor becomes 1. So at x is equal to Wn, we get Jpwn is equal to Q dP by Lp into Pn naught divided into exponential QVA by Kt minus 1. Similar expression you get for the electrons. Again you need to solve for you need to first get the diffusion, you need to plug in the value of delta Pn in terms of exponential QVA in the diffusion equation in the continuity equation, and then you apply the boundary condition just like we applied in case of electrons for the holes. And when you apply the boundary condition, after applying the boundary condition you get this, so you get this expression delta Np x double prime is equal to Np naught exponential QVA by Kt minus 1 into exponential of minus x double prime divided by ln. So they are similar equations, it is just that you replace n by p and p by n, that is it, and the positions are different. So you just then again you do the simple thing, you since we want to calculate Jn at minus Wp, you replace x double prime by, so at minus Wp x double prime is equal to 0. So hence this Jn at minus Wp is nothing but q dn divided by ln into Np naught into exponential QVA by Kt minus 1, and then you sum them up, and what we get is the famous diode equation that you obtain, and that is what gives you the exponential relationship of diode current. So, this is the analysis that we have done in dark. In the next class, what we will do is that we will take this same analysis forward by applying a light term to it, and we will see what we get in terms of a PN junction which operates in light conditions. That will set up the framework for photovoltaic junctions. Okay. So, from the next class onwards, we will be moving into solar photovoltaics in real sense, because we will be looking at PN junctions in light. All right. So, thank you. So, we will meet in the next lecture.